Log on, tune in, find out. Another good idea from Cambridge.
David, so good afternoon from me too. I'm John T. Ruger and I'm chairing this afternoon's sessions. And I think probably without hanging around at all, we'll move straight on to a joint presentation from Kevin Horsburgh and John Huffnance on the programme today.
Thank you, John T. Thanks for coming, everyone. I'm Kevin Horsburgh, and I'll be giving this presentation jointly with John Huffnance. We're both from the National Oceanography Centre, and we're, among with several others, the joint organisers of this programme. What we wanted to do in this initial talk, without going into too much detail, is briefly review what the programme's objectives were, ask ourselves how far we've gone towards meeting some of those objectives, tell you, the audience, some of the specific things that we've done within the programme, because I'm conscious that not everybody within the audience has been a participant throughout the programme. And then towards the second half of the talk, as well as outlining the emerging themes, I think John's going to say something about the week ahead of us, the final workshop. And thank you to Tim Palmer for letting me steal your opening slide. We felt that it was quite an appropriate one. This is the one that Tim gave at the workshop in London recently. When we set out to create this programme here at the Isaac Newton Institute, we provided some justifications for this programme, and one of those was to try and tackle what are clearly extreme positions on what many people commonly refer to as the climate debate. This is something of a polemic. If you trawl through the internet, you can find sites that are largely managed with contributions populated by real climate scientists like some of us. And then there are other sites which are perhaps clearly very antagonistic towards the climate science that goes on. And we said when we constructed this programme that these extreme positions arise because of the uncertainty surrounding some of our knowledge and some of the things that we're able to say about climate science. And that's what we wanted to tackle. We wanted to address that particular problem. And when I was putting this talk together just over the weekend, I found some classic examples of this very thing. Once again, people are confusing weather, the short-term phenomenon that we've been experiencing for the last week or so with climate, and using that as a rather sort of fallacious argument against global warming. And similarly, this is an article which is on this real climate internet site, written by Stefan Ramsdorff, which is simply an expose of a piece of journalism based on the assumption that thermohaline circulation may stop, and then presented to the public as though it were some actual expansion of the present year's observations, whereas in fact it was never intended to be that. And so this debate within the blogosphere, if you like, is something that I personally feel is a distraction for real scientists. And one of the things we wanted this programme to do was direct our energies and our intelligence towards addressing some of the real issues and towards building the relationship of trust between the scientists and the people who depend on our results. Again, when we put the programme together, we put some words down about what our aspirations were, and on reflection now, when I looked at those, I realised that they were not very well thought out. We talked about reducing uncertainty, because that's often spoken about in climate predictions. In fact, by increasing your knowledge, there are possibilities where you can actually increase your uncertainty. So, for instance, you can become more certain about a greater range of variability. So we need to be very clear about the language that we use. Does that mean we're actually building better representation of the Earth, atmosphere, cryosphere? Not necessarily. One thing does not necessarily infer the other. When we talk about properly assessing, what on earth does that mean? And how are we better interpreting the output? And all of these things are somewhat better understood when you start to dress it in a consistent framework, and that framework is to a large degree statistics. And on reflection, I thought perhaps we should never have written those words, and a better way of expressing this would be to provide those people that need, that is the policyholders, the public, some believable, credible, systematically derived, where it's clear what you've used, and absolutely transparent assessment of the uncertainty that remains within our predictions of climate over whatever timescale is of interest. And that, I think, is what policymakers and what the public and probably what newspaper editors want to hear from us. They want the honesty, and this results in a sensible dialogue rather than an antagonistic dialogue, where we're answering the appropriate questions rather than the ones that are more convenient, and also having the courage to point out when certain questions are unanswerable or when the answers contain such tremendous amounts of uncertainty that they're not very meaningful and not very usable. So one of the things I think we hope that this programme over 4 months has achieved is a small step towards that honest dialogue. The programme had two primary sub-themes, and one of those was looking at stochasticity, the creation of physics models at the sub-grid scale in the AOGCMs, the large climate models, that better represents the full variability of the unresolved processes. So, for example, cloud physics in the atmosphere or the eddy fields in the ocean. And our first workshop was largely concerned with stochastic approaches to this, with a view to improving the variability of our ensemble climate simulations, making connections between the large general circulation models and statistical tools, and indeed between simpler models, the so-called Earth systems models of reduced complexity or intermediate complexity. And of course to develop the framework and the statistical techniques that give us the basis for making probabilistic climate predictions which are meaningful and which are useful, and that was the purpose of the second workshop, which was held remotely in Exeter. Because of course the amounts of model data are huge, and we wish to pose quantitative assessments of what that means in order to provide useful probabilistic outputs, and also, this is very important, how we might best use measurements of the real Earth system in order both to assess the climate models which we're using and also to initialize them through the process of data assimilation, because increasingly now we're using those models at better resolution. Tim Palmer will talk later about the issues of resolution within climate models, but increasingly now we're looking towards seasonal predictions, decadal predictions of key climate variabilities, and that actually facilitates the use of data assimilation techniques in climate models in a very similar way that we do currently in numerical weather prediction models for the shorter range. And our overarching goal, and what's clearly been achieved by this workshop, was to bring together some world leaders across some very different disciplines and to have them start to talk to each other and understand one another's language. People that have been to the programme and have left are asked to fill out a sort of leavers questionnaire, and John and I quickly looked through those questionnaires to give us a very quick view of what we've achieved. And we found some very interesting quotations. This from Hugo Lambert in Exeter: the best way to do statistical climatology is to work with statisticians. Something else that became clear from our programme participants is that they've been exchanging views rather freely with the other programmes that have been going on here in the Newton Institute, and that's a tremendous advert for the proximity of working together. And the final one there simply makes the point that because of this forum, because of this method of working, people have had the opportunity, almost as a pre-review, to get some very constructive feedback on work in progress and to improve it and to move it forward pre-publication. So it's almost been like an instant review process too. Again, thanks to Tim Palmer. I borrowed this slide from Tim. This is a slide that sort of shows the interplay between, if you like, the real world, our most computationally expensive tools, the atmosphere, ocean, general circulation models, and many other simpler mathematical tools, both of which we use to derive meaning from that reality. These mathematical models and these very expensive computer models both have a role. They're both used in a sense to inform how we respond to the threat of climate change and to inform policy. Oops, sorry. The important point, of course, is that this programme has brought the different communities together, from the people looking at simplified dynamical systems models, where through some fairly simple but highly nonlinear equations you can see transition states which appear to be very much like the glacial interglacial cycles. It raises some interesting questions. perhaps provide some insight for how the real world operates. But there's certainly more work to be done to show that that's more than simply mimicry of the system, that it does actually have some genuine connection to the system. The other important thing about connecting the disciplines, which we think we've achieved throughout this programme, is that we've learned to use meaningful language. The word model, for instance, many statisticians feel to be overloaded. A model can be anything from one of those to a simple statistical regression. Statisticians are quite happy to throw away a model if it doesn't meet certain criteria, if it fails certain tests. We clearly can't afford to throw away these. So increasingly we talk about these computer models of the real world as simulators, and later on I'll introduce the concept of emulators as well. The important thing about simulators is they do aspire to represent all of the processes in the physical system. They're, if you like, discretized computational versions of the real world. But simulator, like a flight simulator, tries to behave properly when kicked in the right direction, and then emulators do not in any way aspire to have all of the processes in, but simply in a statistical sense to describe the same space as the simulator, which they can explore in a more computationally efficient way. This is something that newspapers do when they're trying to simplify a big topic in numbers. So this is our programme in numbers. 157 participants have registered over the course of it. It's gone on for 19 weeks. So if you take out the weekends, there's been 95 days of scientific interaction between those different participants. Something like 150 hours of formal presentations and probably 10 times that of informal discussion up in the coffee room. Again, referring to the questionnaires and the reports that people fill in when they've finished working with this programme, on average people are reporting between 2 and 5 collaborations stimulated by their time here as part of the Newton Institute programme. So clearly this is going to lead to lots of papers. It already is leading to grant applications, and in a nutshell the programme has provided, I think, an unrivalled opportunity for cross-disciplinary research into climate. So very briefly, some of the things that we've done. We had a workshop here to kick things off, largely focused on stochastic methods. All of the talks, all of the videos of these lectures are available if you go to the appropriate website. This particular conference is, some of the talks are leading to papers in a special issue of Phil Trans. There was a satellite workshop at the University of Exeter. There was a one-day event which David referred to in London, where we used the Willis Insurance Building, and we convened 2 panels of experts, one largely based on the science, one largely based on climate policy and energy policy. And that was a very, very interesting event where it became clear that there was a lot of mutual respect between the scientists there and the people that depended on the results. And then, of course, this workshop. And along the way, we've taken the opportunity to bring people together for informal gatherings. So we've spoken. We had a day on emulators, more of which in a moment, and particle filtering. We've had special get-togethers on the issues of paleoclimate and its interpretation. On the issue of tipping points, so that's sort of irreversible changes in some key feedbacks between the different parts of the climate system. A meeting with the Royal Statistical Society on complexity, and a meeting on multi-model ensembles and approaches to probabilistic climate projections in general. And so all of these things, if you go to the website, you can find the results of our labours. So now I just want to move things on a little bit. John and I, between us, will talk about some of the emerging issues. So I'm going to go as far as paleoclimate, and I'm going to hand over to my colleague, John Husnett. One of the things that the statistical backbone of this programme has provided is a framework for properly understanding the complexity that is climate science. It provides a way of bringing together models of different generations, models that use very different amounts of computational effort, and it also brings together inevitably the expert opinion that's required to make judgments about those models and weight them. So uncertainty frameworks, which are necessarily statistical frameworks, and this is from the Exeter workshop, try and provide answers to some of these rather key questions. Where do the uncertainties come from? Which climate simulators should we use? How do we weight them? What are the appropriate statistical frameworks? And there's been much debate about that, about whether we consider the data as fully exchangeable or things like second-order exchangeability. And all of these are degrees of weaknesses of the assumption which are necessary in order to provide the right statistical framework for making progress and integrating the results of many, many different models. And then, of course, how do we correctly interpret the information in a way that's suitable for the people that need the answers? This is really just an advert for some talks that are going to happen tomorrow from Jonty Rougier, from Michael Goldstein and from Richard Chandler. They will be exploring in detail some of the interpretations of ensemble experiments. I just wanted to bring to your attention the fact that for 2 weeks I think Arthur Dempster participated in this programme and explored the possibility of statistical systems where we allow the propagation of don't knows. And this is very important in climate, is whether or not it's tractable, whether you can allow some probabilities which sum to less than one. A lot of work, I think, needs to be done before we can make progress here. Conditionalisation with probabilities that are inequalities rather than equalities is enormously difficult, and the computational overhead of this approach is daunting. This, I think, summarises the feeling of the statisticians that contributed these slides. We need to carry on what we've been doing. We need more application of statistical frameworks with the climate modelers, more interactions such as we've had during this workshop. We need to build statistical design into climate model experiments from the outset, and to some extent this is already being done with the ensembles that have been run as part of our own contributions to IPCC, with the EU Ensembles project and with the American NARCAP project. So increasingly statistical design is forming a plank of model experiments when they are conceived at the point of conception. And of course we need increasing dialogue with the end users to understand what levels of uncertainty they can deal with as a matter of policy. And this was something that came out of our workshop in London, our public dissemination day, is the amount of uncertainty that we are often fearful of is something that policymakers can handle rather well. They have actually got tools for dealing with large unknowns. We needn't think that just because our answers are imprecise, we can't hand them over to the people who need them. There are other tools for dealing with probabilistic information and for decision making. Not surprisingly, and I won't go through all of this, statistics has been the backbone of the programme. That was the intention. Right from the interpretation of relatively simple phenomenological models of complex systems, through to larger problems, through to the use of statistical methods in paleoclimate and the way that we deal with large ensembles, and the various participants are listed there against the contributions that they've made. And an important point to make here is that as well as statistics and mathematics providing the tool for the interpretation of climate, so statistics is helping climate modelers and climate scientists, these problems are also challenging the statistics themselves. So the climate problem is allowing the advance of statistical methodologies. So it's a mutual exchange. Statistics are benefiting climate science, and the challenges that are posed by climate science are forcing the statistical methods to move forward. Excuse me. So it's a truly sort of beneficial exchange in both directions. Matt Collins later on is going to talk about probabilistic projections. One of the methodologies which he'll refer to and compare with others is a recent methodology that Miles Allen and some co-workers have put forward, where they use observational records to scale both spatially and temporally, and then they can recalibrate climate model output. So this is just an example of what can be achieved by these methodologies. The solid line there is an original climate model output. The dashed line there is recalibrated when certain observational constraints are placed upon it. The grey band are just the normal percentile uncertainties of the original model runs, and the observations there are shown in red. So this is something that Matt Collins will elaborate upon later on. And I think what we're trying to achieve here is to move forward from IPCC style interpretations of model ensembles, where they perhaps take the mean and the variance and then just assume that there is some sort of meaningful interpretation of relatively simple statistical properties when applied to regionalised climate problems. We need to have a more sophisticated approach than that, and this is something that Matt will follow up. This is the use of rank histograms to see whether or not the spread within a model ensemble is in some sense too wide or too narrow, and if the spread were ideal, then these histograms would be flat. But that of course also raises the interesting question, what is flat, and is there a suitable test for flatness, because we're dealing with relatively small sample sizes here. There was a particular day set aside where some discussions were had on this methodology, the so-called ASK methodology, due to Alan Stott and Kettleborough. So they take some outputs and then they use scaling factors to try and make adjustments that are associated with particular forcings, such as volcanic ash, the solar cycles, and so on and so forth. There was a lot of debate about the applicability of these methods compared to some of the other statistical methods, but the important thing is that when you're interpreting climate projections in a statistical sense, that you're absolutely clear and upfront about what the methods are that you're using, which brings us back again to the need for rigour and transparency in everything we do, obviously with our stakeholders, but also with each other. And this really is just a brief overview of the talk that Matt's going to give later on. There's a clear tension, isn't there, if you've got a certain amount of computer resource available to you, between the resolution that you might want to go down to in order to properly resolve all physical processes, and the size of the ensemble that you can run in order to give a statistical assessment of uncertainty and make some progress towards understanding risk and the calculation of extremes, to have sufficient spectrum that you can get extreme events from it. And clearly, if you've got a finite computing resource, then you can't enjoy both of those things. So Peter Cox, one of the co-organisers of this programme, and some co-workers in Exeter, produced some interesting mathematical analyses for this problem here. So this is that same thing represented graphically. You can have a greater realism of physical process on the Earth, or through a larger ensemble size, you can have a better estimate of uncertainty. But if your computer resources are limited, then you can't have both. So it poses an interesting question, to which we didn't get the answer, but we made some progress towards whether there might be an optimum position arrived at through either analysing the existing climate model results or even from mathematical first principles. So that's quite a useful steer towards where you might direct your computing resource. There will be a talk tomorrow from Peter Challoner about emulators. An emulator, for those who don't know, is a statistical approximation to the original simulator. So I'm using the word simulator here to represent a complicated computational representation of the Earth system, like HADCM3, for example. There are different ways of arriving at an emulator, but in a nutshell, you have to run simulator experiments. You can't dispense with the simulator. Although the emulator has many roles, it's a useful tool. It won't replace the fundamental GCM that it's emulating. So you can build it, and then what you can do with it in a computationally efficient way that you can't do with the simulator, because you can't run a big enough ensemble, is you can then draw inference on aspects of the parameter space that you weren't able to visit with a finite number of ensemble simulations. So here's an example. This is a relatively simple nonlinear process x sine x or something like that. So you can just take 4 points on a nonlinear process and then build an emulator which should, but doesn't, apologies, the slide hasn't worked, build in envelopes of uncertainty. So the dotted lines that haven't come out here are actually... Pardon? Are they? I can't see them. Right, oh yes, there they are. You're right, yeah. So in fact the emulator builds, as well as sort of building a simplified model of the statistical properties of the simulator, it does, if you look carefully enough, provide you with the uncertainties. Some progress has been made, so this is just to summarise progress on emulators. Even with very nonlinear functions, then it's possible to design emulators, some work that Peter and Robin did. And Bayesian training for neural networks also leads to emulators in the same way that Gaussian processes do. The talk I think that Jonty's going to give tomorrow is going to focus largely on emulation of the HAD-CM3 output, so that's something which will be covered in considerably more detail. This is the last section of my brief overview, and time's about right for this, so I'll quickly go through the role of paleoclimate. And thanks to Michel Crucifix for these slides. Paleoclimate is a tremendous asset in that it provides us with the length of data set which really allows us to understand some of the true behaviour of Earth's climate system, far more so than the observational record, which although highly accurate is relatively short-lived. So through paleoclimate, if we can make progress in its interpretation, then we can certainly make huge inroads into understanding how the real climate system works. In terms of reconstruction, problems of dating, because very often we try and take, as the next slide will show, something which is not directly age-related, and then we have to transfer it into an age-related variable. Paleoclimate, of course, provides us with some identification of rapid changes in the climate system, or the transition from one to another state in a multi-state system. It allows us to quantify those uncertainties. And so we've had many, in fact, a large part of the initial workshop focused on paleoclimate. There are, of course, many statistical techniques which have tremendous utility here. Particle filtering, approximate Bayesian computation, and emulation again. And skip that one. There was a day in September when the SupraNet project, which is studying uncertainty in paleoclimate, combined with our workshop to talk about proxies. Proxies in this instance are things like fossils, things like isotopic ratios of oxygen in ice cores, things which lead us to understand changes in temperature, but indirectly. And thanks to Caitlin Buck for these slides, reconstructing the climate on the basis of these proxies is very complicated, because we're using those as substitutes for the physical variables that we want to understand, and of course we're not directly measuring these things, we're inferring them. So we're inferring the properties of temperature, precipitation, from things like pollen and from things like chemical isotopes. And typically when we drill down through a core of mud or some such to get these things, then the record itself is on the scale of depth, but of course it needs to be placed back into the scale of time. So this in itself presents challenges, and each proxy has a different transfer function between depth and time. So there's a complication there when you're trying to make many proxies come together in a multivariate analysis of the past climate reconstruction. And that's the challenge of SupraNet. Hitherto, most proxy scientists have really tried to zoom in on what is the most likely climate, but without really considering the uncertainty. But of course you can't avoid the uncertainty when you wish to bring different analyses of different groups, different proxies together in order to have a single understanding of the paleoclimate system at, for instance, a common geographical location. And this just sort of shows the complexity of the problem, and I think makes a very obvious point that you you shouldn't regress cause on effect when there's a very complicated process in between. So here, for instance, is pollen, and here, of course, in a sense, is the temperature that is in some way related to that. And in between that are some very complicated processes. And emerging from the SuperNet findings is a way of using large Earth systems models in order to generate candidate climates. So you run the model in order to arrive at some values for the proxy. For instance, it might be a pollen type, and then using this rather computationally intensive approach, you can then say something about the distribution in a much more meaningful effect than making a false regression. So I think there's a lot of progress being made there. I know there's a lot of papers being written by Caitlin and Jonty and the people working on the SuperNet project. And I think this is where I hand over to John for the second half of the talk.
Thank you, Kevin. Am I switched on? I think I better begin with a couple of apologies. Firstly, distractions which may make this part of the presentation slightly less fluent than it should be. And secondly, that I'm talking about quite a wide range of fairly technical matters, and I'm not an expert in all of them, certainly perhaps not in any of them. I must thank the contributors who I hope have acknowledged in a typical way at the top of the slides that follow. So firstly, this is connected to what Kevin was referring to. How do we interpret the IPCC models? Do they actually have enough internal variability to provide the right test of whether we're actually seeing climate change against that? Process has been used to investigate that question using observation-based stochastic models, and a plot here with 3 of those models showing a distribution if it was all due to natural variability. And I think, oh dear, another faint line, I'm afraid. There's a faint line here indicating the actual observed trend being well over to the right of this distribution, and therefore improbable if it was just as a result of natural variability. So this is going to lead to future collaboration between participants of this program to evaluate the relationship between trends and internal variability in IPCC models using these techniques, and also maybe Madden-Julian oscillation and ENSO behavior of the Met Office seasonal climate model in a similar way. Another theme much discussed here is tipping points and how you may detect their coming. The record here is an oxygen 18 from GRIP ice core on the left and NGRIP on the right. I think the main figure in a way is this one. This comes from Tim Lenton, and they have been looking at how many background states there may be at any in different periods through these records, period 1, period 2, period 3, and so on. And there's a colour scheme for the number of states. Green is 2 and red is just 1, and there seems to be a transition between 30 and 25 years before present from having 2 to having 1, looking at the statistics of these records, and they've inferred sort of potential well-type function indicating 2 stable states here, one obviously a bit less stable than the other, but transitioning to just 1 for this period 4 here. Looking in more detail at the GRIP oxygen record just between 22,000 years ago and 12,000 years ago, And looking at the detrended record, you see these oscillations, and you see a change in character of the oscillations towards larger amplitude and lower frequency, and this is interpreted as an early warning of the coming of a change of state, loss of stability of a glaciated northern hemisphere, and there's a lag-1 autocorrelation function here being used as an indicator from this series. Chris Huntingford has also been working on a related question. He has a simple theoretical model of rainfall in relation to land surface cover with trees, basically. For example, the Amazon forests. You can reduce the rainfall until the feedbacks mean that you don't have a forest anymore. But you can also look at noise in the rainfall to see how that relates to the tree cover. And this has led to some equations to consider the slowdown in the oscillation effect of the previous slides. This is just for one patch, if you like. There are plans to consider interactions between different patches side by side, and has also been looking at a first order statistic to investigate when significant changes of temperature look as though they're going to come. So Hadley sent a climate model here. Temperature, is that a precursor of actual major changes predicted with the model? For example, Amazon dieback or polar migration of the boreal forest. A change of tack now, because in a way up to this point was, if you like, statistical approaches. Now I'm actually going to say a little bit about what people have reported back about progress in the numerical modelling aspects in various ways. So this from Mike Cullen is about, if you like, mathematical schemes that one use to help progress GCM calculations faster than they would be if you explicitly integrated all the equations. Geostrophic balance is the balance between pressure and the Coriolis force on the flow, and it applies to, largely speaking, large scales in time and space. But Mike has found that it holds to a smaller scale than you would a priori expect, because of the way in which damping from smaller scales actually operates. And this was an interesting interaction, in fact, between the climate program here and the the KIT program, which has been going on at the same time. Another aspect here is blocking climatology and the influence of the stratosphere. The stratosphere structure affects the radius of deformation for features on the whole depth of the atmosphere. And because a smaller radius of deformation resulting from this stratospheric effect is likely to make blocking more frequent, then there is an influence of the stratosphere on the blocking frequency potentially here. And this has been done by analysis of the shallow water equations. He's also made further progress in proving that semi-geostrophic equations can be solved rigorously in spherical geometry. I think Mike's been advocating these equations for some time. But they are a better alternative to quasi-geostrophic theory, which is used a lot, but in fact has a rather inconsistent breakdown on the scales at which it properly operates. And so he's recommending stratospheric, semi-geostrophic equations as a simple model of the large-scale atmospheric circulation. This, thanks to Paul Williams, who is speaking on Wednesday afternoon, illustrates that model numerics are themselves a source of uncertainty. This is a histogram showing the distribution of states of the Lorentz attractor from the famous paper in 1963, different if you take a crude time step from if you take a presumably well-resolving time step. So these are quite different distributions of the state, and simply due to the time step. This, thanks to Serge Vilas, is about prospects for climate chemistry modeling. There are lots of parameterizations in a physics-only model, and you go to chemistry, there are more, and you want to have means to check those parameterizations are appropriate. This has benefited much from discussion here about experiment design and Bayesian calibration process to help run models. So this is in the future. Again, an influence of the stratosphere on tropospheric processes, that stratospheric water vapor affects stratospheric temperature and tropospheric temperature. And a decline in the stratosphere. Stratospheric water vapor translates here to a decline, or decrease, I should say, in fall in tropospheric temperature. So stratospheric water vapor decreased about 10% since 2000, and this has been estimated to affect the global surface temperature rise, in fact, reduce it compared with what it might have been. This is an effect of different greenhouse gas effect. And just some plots here with 8 different models and of profiles of temperature trend through the depth from the top of the atmosphere to the Earth's surface. So there are 8 models here. This is 90 south to 90 north, these two. This is the tropical range in the bottom, and the top plots are, sorry, I beg pardon, the left-hand plots are 1980 to 1999, so that's the past, and then the right-hand plots are mostly the future. So there's some details here about the way the models were run, but this is an indication of the temperature trends, and but the chemistry will have an effect on these. Peter Challoner is talking tomorrow afternoon, and we'll say more about this. Now we're going on really to discussing how even a general circulation model doesn't have all physical detail, and how you may represent subgrid processes better in a physical model. So this is if you like, mostly philosophy, but Peter will say more about this tomorrow afternoon. We have a GCM that can't resolve the subgrid scale processes, obviously, but we do have a more detailed model that can do that, too slow to embed. So the idea is to build an emulator for the process model and embed the emulator in the GCM in a deterministic or stochastic way. Peter's been thinking about this. In fact, Dan Cornford and Judith Werner are exploring this idea for parameterization in relation to clouds. This thanks to Bob Plant, continuing this theme, but not particularly with emulators, but with stochastic parameterization for subgrid processes. In a typical climate model, you'll have lots of individual clouds, or maybe as the resolution improves, you'll have rather fewer individual clouds. If you really have a large number, then maybe you're okay representing this with just one mean and some variability, well, one mean in a grid box. But if you have moving towards finer resolution, then clearly it would not do to have the same representation in all these individual grid boxes. It could go from none to quite a lot in different grid boxes. So you want to estimate the variability as well between your grid boxes. So you need some theory for the mean strength effect of the cloud convection and the fluctuations. So there is a parameterization for this, hitherto applied in single column models and for ensemble weather forecasting, but based on equilibrium and not applied yet to climate models. Here's an example of clouds in a UK Met Office forecast with scattered character. Here actually is the theory, which is the smooth red line. Yes, smooth red line as compared with observation statistics for distribution of convection scheme on this equilibrium theory. So some outcomes from the program in this topic. Schemes have been sent to NCAR to try out on their climate model, and Bob is trying to develop a theory to model convection that's out of equilibrium yet still account for stochastic nature. So you realise that there are problems with previous attempts to do this, and that benefited from the parallel program. Well, sorry, I should say from the dynamical systems thinking, which was an element of our program. More work still to be done, but he thinks he may have made good progress here. And also on a related topic, Judith Berner and Joe Trebbier have been looking at twin experiments with fine and coarse resolution for backscatter from unresolved scales to give a stochastic potential vorticity flux from the subgrid scale to the resolved scale in the model. Also, in relation to the turbulence spectrum. So, for example, rotation has a well-known influence on the turbulence spectrum. So here is the spectrum in the inertial range and not affected by rotation, but then you come to longer scales and rotation has an effect on the turbulence spectrum. So this sort of understanding should inform the way that the subgrid turbulence is represented in large eddy simulations. That's being pretty ambitious if you're talking about climate modelling, but anyway, the smaller scale to the larger scale. So the approach is consider how external agencies modify the energy spectrum and then derive subgrid models consistently based on the modified spectrum. Yes. And John Thuban as well been looking at this. This is actually about vorticity field, and so here is a calculation in all detail. In fact, about 4 megabytes of picture here. So this is vorticity from relatively fine resolution integration of the barotropic vorticity equation. If you have the fine resolution, you can calculate the energy tendency at every wave number. If you truncate the spectrum to wave number 96 and again calculate the energy tendency at every wave number, you have a difference. For wave numbers greater and less than 96, you have the difference due to the presence of the wave numbers, the larger wave numbers or shorter scales. So these plots show the difference actually here for energy and here for entropy, as found out by this, if you like, proper calculation. And then here below is the difference across the wave number range. If you used a del squared or del 4 scale selective dissipation as, if you like, your parameterization. And you can see especially here that there's the effect is too broad across the wave number range in these plots compared with what it should have been in the top plots. So these del squared and del 4 are commonly used, but they dissipate energy and entropy over too wide a range of wave numbers and fail to capture the backscatter of energy into small wave numbers, large scales. So participants are looking at whether stochastic subgrid models can do better. And there's more about this subject generally of stochastic parameterization in Tim's lecture, I think. Maybe. Maximum inventory production is definitely somewhere where I'm not qualified to speak, and hopefully Peter Cox is going to be discussing this tomorrow afternoon. But I have to report it in the sense there's been a lot of presentations and discussions about maximum entropy and maximum entropy production, and it has potential to provide general constraints on complex stochastic systems. But there are perhaps questions about when you will have the confidence to apply this ahead of time. Now a couple of slides about more I'm not going to say this right now, but from a dynamical modeling approach, stochastic model production, and we've had some talks about this, and so they've been discussed here, although actually the rest of this slide really is about application in other fields. But there is an interesting result to report here. If I go to the next slide, this is a simulation of a Hamiltonian system with a quartic double well potential and different values of the parameter epsilon. And oh dear, the left-hand side hasn't come out, but this is sort of mirror image of the right-hand side, and you can see a trend from large epsilon to small epsilon clearly in the character of the space explored by the solutions over a particular length of time. The whole space is explored even for large epsilon if you have long enough. But anyway, the point is that as you get to small epsilon, it looks very Langevin-like, and there is a proof that the Nuss-Hoover, I hope I've got this right, Langevin equation reduces to the Langevin equation as epsilon tends to naught. So I will move on.
Explain that a bit more?
Pardon? No, I can't explain that a bit more, and I will appeal if anyone does have a question that someone owns up to understanding this better than I do. And also about data assimilation, this is not data assimilation, I suppose, quite as a serious numerical modeler would think of it in terms of initializing a GCM exactly, but data assimilation in more a Bayesian sense and moving from your prior distribution to your posterior distribution. If you take this point of view, then you have a transport, if you like, from the prior to the posterior. So theory about that process gives you a transport map, and the point being made here is that although assimilation techniques as used can be put in this framework, the transport map approach is not restricted to Gaussian type distributions. Initial studies have been performed pursuing this idea. So that came from Sebastian Reich, but also from Joe Tribbier and Michael Gill. They've been looking at, or will be looking at, hybrid ensemble variational data assimilation as a means to get to an optimal state for prediction from. And Jacques Finest also has been thinking that he can make progress, again, mostly in the future, about thinking about data assimilation and whether have a mathematical formulation for assimilation in climate models. So you can think of the equation covering the probability density governing the probability density distribution as a basic equation for climate studies. So you're evolving the PDF. So the state of the climate system is a probability distribution function. The observations provide information about this, and assimilation should lead to the best estimate. Normally, assimilation involves an ensemble of solutions. So for climate assimilation, you're considering an ensemble of PDFs. So you have a probability distribution of the climate PDFs. And this ought to be governed by something like an infinite dimensional Fokker-Planck equation. So the plan is to study a simple model, obviously not infinitely dimensional, with weather as a finite state system. And finally, in this sort of section of the talk, an alternative to Eulerian formations for the dynamical equations that you integrate. if instead of going directly from Eulerian equations to your ordinary differential equations by discretization, you go to a Hamiltonian formulation and discretize that, and then go across to your set of ordinary differential equations. You may hope to build in more conservation properties. So that's the schematic, and this is just an example of using the approach for rising and sinking bubbles, which I think I can move over. So the progress in this respect is that the schemes have been developed for shallow water equations on a sphere, and non-hydrostatic and hydrostatic vertical slice models. And benchmark tests show that the approach can represent atmospheric flows and conserve energy accurately long term, and experiments are going on in introducing other processes now. So the rest of this workshop, today you have Matt Collins' talk to come and the Rothschild lecture from Tim Palmer. Tomorrow is largely about past climate and emulators and uncertainty and probabilistic aspects. Wednesday is primarily about models. I have to apologise for withdrawal from your programme owing to a family bereavement, so Stephen Belcher's talk will not take place on Wednesday, even though it's on your programme. Then Thursday, with some spill over into Wednesday actually, is about stakeholder interests. Not preaching to stakeholders, but effectively trying to tease out what they want. And then we'll have wrap-up discussions at the end, mostly on Friday. So the aims of the discussions on Friday and leading up to that are to encapsulate the findings of the programme, perhaps more synthetically than I've presented them, how to disseminate them, and how to progress work in its various ways in the future. So thank you.
Right, thank you, Kevin and John. We do have a little bit of time for questions, although obviously more specific questions will need to be directed to the appropriate people during the rest of this week. But if we have any general questions that we might ask about how the programme has gone so far and where it's going to, and if, when you ask a question, you could state your name for the record.
Hi, it's David Wallace. I found that a very helpful overview of what's been going on. I know I ought to know, but that was very good, and thank you. Just to fill it in a little bit, and I don't know if this is for Kevin and John or for somebody else. I have understood that water vapor and clouds are one of the most difficult things to deal with. Now, you did talk about water vapor and how, if I understood rightly, a reduction in stratospheric water vapor would actually result in a reduction of the increase in tropospheric temperature. Do I understand that 10% reduction in one, which we might have observed, 25% reduction in the second? Now, is this the beginning of understanding the effects of water vapor, or am I just way off beaming that? Remember, I'm a non-expert.
I'm not the expert either. I'm looking for Serge. Is he here?
I'm not
Yes,
the
he
expert either.
No, but I think
that's
I've got
that's
that
a
from you.
paper by Susan Solomon in Science. Yes. And yes, there's many interaction. And modeling better is definitely important. At the end of her paper, she advocates for more effort in terms of modeling. We don't understand yet fully what's going on. Maybe someone else can.
I could probably just comment that, David, in terms of what we call the tropospheric water vapour,
Yeah.
the water vapour that's low down, there's a sort of well understood feedback between that and, so as the temperature goes up, the amount of water vapour the atmosphere can hold goes up. It's sort of simple physics.
Right.
The issue under question here is the role of stratospheric
Right.
water vapour, which has an impact on the radiation stream in such a way as you described. And that is much more uncertain at this stage.
So my question was the kind of results that John, I think it was talking about are the beginnings of understanding of that, or am I being, or have I misunderstood?
I would probably say in terms of the stratospheric water vapour, there's issues, for example, about how water vapour gets into the stratosphere, how it crosses the triple pores and things like that. So yeah, probably is the beginnings of that.
Well, Tim Palmer, just a comment, well, two comments really. I mean, actually, the talk I'll give this afternoon will actually be more about those sorts of issues, uncertainties in clouds and water vapour, and perhaps what we can do about them to move forward, perhaps, and less about the stochastic parametrization, which I feel I flogged a bit in my first talk at the beginning of this programme. So.
Chris Farmer. I was wondering, had there been much discussion that you're aware of about the question of validating probabilistic climate forecasts?
Actually, we had a breakout group. You were there, the extra workshop. One of the breakout groups.
Yeah, but I mean,
climate model evaluation on the focus
yes, I know,
evaluation.
but in terms of the summary that's just been given.
Well, that didn't appear there. No. It might appear a bit tomorrow. In fact, nobody actually came up with any recommendations from what I gathered. But there was a good discussion on it. 5 questions were. We came up with more questions than answers, right? Which is probably questions are good. So, but, I don't know if you want the summary of questions tomorrow or you want answers.
But I know that Chris Ferro has been working on this within the remit of the institute. But,
Yeah.
I don't think he's here this week.
No, he's not here, and he didn't come up with answers in the breakout. But they weren't. The breakout sessions weren't supposed to produce answers in 3 days. 2 days.
I think David will be saying more about this tomorrow, won't he?
Yeah, I'm in trouble knowing because there's no answers. But if you want to see the questions, I can show you those. Got a growing list of questions. But you're right. How do you evaluate near-term climate predictions is a good question.
Well, perhaps I could just make a remark. I mean, just a couple of weeks ago, we had a visit in Oxford from a guy called Reason Machete, who is working at Reading. And he brought to our attention something I hadn't seen, but some of you might know, papers by Tillman Knighting that were in the Royal Statistical Society, actually discussing the question of validating probabilistic forecasts in a very deep discussion. And he actually gives references to a thread of literature that does go back many years. And I wasn't aware of it.
Tillman's actually visiting next week.
Yes.
Oh, there you go.
But I wonder if that validation is perhaps more aimed at short-range weather forecasts rather than climate.
It is actually on Tolman's papers on whether the probabilistic climate prediction for. But there's been a long history of how do you evaluate probabilistic forecasts. It's not obvious.
Yeah, George Craig. That actually brought up a question that I always thought was really interesting. Is probabilistic forecasting of climate something fundamentally different from probabilistic forecasting of weather? Lorentz long ago defined 2 types of prediction, one that was essentially a boundary value problem, climate, and one that was essentially an initial value problem, weather. And it looks as though the discussion has been tending to perhaps bring those together or blur the boundary. Was there any result on that at the workshop?
Yes, the workshop the breakout group talked about the seamless aspect. And the I wasn't in the breakout on the evaluation, but I think they discussed seamless climate and weather prediction. And they did discuss the differences, like you said, there's differences between doing a climate prediction and doing repeated weather forecasts. Right? So they did discuss that issue about some of the challenges for evaluation of climate predictions compared to weather forecasts.
There certainly is a distinction between, in the sense of whether the initial conditions are the big uncertainty or whether if you like, the boundary conditions, and especially the greenhouse gas content, is the biggest source of uncertainty. But I think also we concluded that there is no timescale at which you can really draw a line and say, well, one side is that way and the other side is climate.
There's some distinctions though, because the climate prediction problem is extrapolating to somewhere you've not been before, whereas weather prediction, you're doing events that you might think you've seen similar sort of things in the past, right? So there is a distinction there, but it's not seamless in that sense. Good question, how seamless prediction is.
Well, it's an interesting question. I mean, I think there are similarities and differences. I think one thing, which often the general public confuses, it relates to what George said about Lorentz's kind of nomenclature. That is to say, even if our weather forecasts had no skill whatsoever, if we could say nothing skillful about the weather in a week's time, that doesn't invalidate the possibility to make useful predictions of climate change in 100 years. But that doesn't mean that the two areas are not kind of closely linked. So, for example, if you evaluate a set of weather forecasts, even in some limit where you think there is no predictive skill, and the probabilities are clearly biased or different from the climatological probabilities that you would expect the forecast to asymptote to in the limit of no more information coming from initial conditions. That bias, that potential bias, well, that bias I think which does exist actually in many model systems, is relevant in helping us understand the confidence we can put in longer term climate change predictions. And I think that's the area where this kind of seamless prediction philosophy is relevant. But it's clearly a slightly subtle issue, and I know people do sort of interpret and misunderstand what this link is.
I think we might break there for tea. So we'll assemble back here at 3:30 by this watch, and let's thank both our presenters again.